Okay, guys, so like I just said, this class is going to be a little bit of a transition class. My goal is just to do two problems. One, covering something we haven't done, but that I mentioned last time. I wanted to give you at least an example. And then we're going to try to do one example with the material we were covering, okay? If you remember the entropy is going to help us do what? To know if a process is reversible or not reversible, okay? But it has been a while because you had the exam in between, so let's do a problem. So basically, what is transient analysis? Transient analysis means that the amount of mass coming inside a control volume is not the same as the amount of mass leaving. So basically, the conservation of mass here, you see here, this is not going to be equal to 0. Okay? And that's the only difference. And I don't like the way, I don't have anything against the way the books solve the problem, but I think it's easier the way I do it, okay? So for example, in this problem, this is the one we're going to be doing. They say that they have a tank having a volume of 0.85 cubic meters, initially contains a water. So this is over here as a two-phase liquid, okay? So at 260 degrees and a quality of 0.7. That's why it's a mixture. Water vapor at 260 is slowly withdrawn at a pressure regulating valve at the top of the tank. So that means you open this valve, you're gonna have some of the steam, but the steam will be leaving, no? The liquid water will be staying. At the top of the tank, as energy is transferred by heat to maintain constant pressure. So what happened? As pressure leaves, the pressure is supposed to go down over here. So what they say is that here the steam is going to leave at a constant pressure. And in order to keep the same pressure, what you need to do, you keep heating this water, so some of the liquid water will evaporate, no? Okay? We'll do a figure. And this continues until the tank is filled with saturated vapor at 260. So now we have another tank here. This is saturated with saturated vapor. So it's the same tank, but just saturated vapor. Determine the amount of heat transfer in kilojoules needed to put to this tank. Okay. So this neglect all kinetic and potential energy, and basically that's what they tell you over here. State 1 of this tank is what? Mixture. They want you to go up to the point where everything is saturated vapor. Okay, that will be this point over here. And this is the figure. All right. So let's solve the problem. So this is supposed to be, so let's see, 87, even though we have 4 pages in between. I have 3 blocks because I have 2 pages on this one. All right, so all right, there we go. So 87, I'm gonna put here transient analysis. So transient analysis occurs when the amount of mass going into a system is different than the amount of mass leaving the system. So basically it means This one is different. Okay, so my only goal here is to give you an example, is not to go into detail. So the example we just had, we have initially the tank over here. Here is the valve. Okay, so initially this would be our system over here. That needs to be heated. But in this case, we have here a mixture inside, a mixture of water, where we know that the initial volume is 0.85 cubic meters. The initial temperature is 260 degrees Celsius. And then the mixture is 0.7. Okay, and in the problem statement, they give us this figure. Basically just saying that step one is a mixture, and here E is saturated vapor. Okay, so here, if you want, I'll show you the solution of the textbook. I'm not a big fan, but basically you see, it says that here, dme mc equal to the amount of mass coming out, which is fine. This is the assumption of the first law. I mean, I don't think it's very well explained, okay? I don't know if you follow, if you follow what they say, but I'll do it a bit differently that I think is a bit more clear. All right, so like always, what is the procedure? You need to do a figure, and from the figure, write down the equation, no? So in our problem here, we're gonna take for the below system, and leave here some space. So initially, what type of system is this? This is a closed system, no? Yeah? So if it's a closed system, what is acting on that closed system? We're gonna have heat, but what is different here about this closed system, what I need to recognize is that due to the valve over here, once you open it, what's gonna happen? You're gonna have some energy leaving. Okay, so here, this is the tricky part over here, is that when we deal with closed system, what are we dealing with? Are we dealing with internal energies, or are we dealing with enthalpies? Remember, I make on a page. I don't have it here, but if you deal with closed system, always remember that you deal with internal energies, and you'll be using C sub V's. If you deal with open system or control volume, you will be dealing with enthalpies, and that will be related to the C sub P. Okay? So what should be the energy leaving here by the pressure? This should be here like an open system. It should be M dot H sub A. Okay, so let's say here, writing the first principle of thermodynamics, and this is the tricky part, but this is a closed system. So we have a closed system, the equation should be what? Q minus work plus what? Plus whatever energy you have on the system, plus M1 U1. This is a closed system. And now what's going to happen? You're going to have M2 U sub 2, because the mass is different here. Now, if this closed, it should be 1. Let me check here. No, it should be 2. Should be different. Okay. Now, and what else is leaving from the system? Plus M H sub A. But now, what is the problem? This one is a mass, so this one is in function of time. Okay, so this one is really in function of time. So maybe we can do, and this will be M sub 2 or M sub E. So if this is a function of time, we need to put all that equation in function of time as well. So we need to put a dot here, a dot here, a dot here, and a dot here. Okay, so let's slow down for a second. So what I'm doing here is what? This is the closed system, no? How does the first principle of thermodynamics apply? Is Q minus work. Is it any work in this system? Don't have it, so this should be 0. We can do it right away. Now, plus, what is the change in energy between the initial state and the final state? This one should be M1 U1 at the beginning, and at the end you have M2 U2 or UE over here, plus whatever the amount of mass is leaving. Okay, and I put it on this side because it should be negative. Okay, now all this one should be without dots because the first principle, supposedly there is nothing moving. But in this case, since it's moving due to this term over here, I put the dot everywhere. And basically, that's what the problem is. That's it. It's basically we got this. So now we're gonna get that Q. One more thing, Q dot will be equal to what? Will be equal to M dot 1 U1 minus M dot 2 U2 plus M dot E H sub E. But now, maybe without going into too much detail, because again, this is just for an example, it will be M dot 1 U1 minus M dot 2 U2.
Isn't it M dot 2 U2 minus M dot 1 U1?
Should be, yes, I move it to the other side. You're correct. It's N2 minus 1. Sorry. You're right. Correct. I was paying too much attention to this time. Now, using common sense, what should be the M sub E? What should be the change of mass here? Whatever is the change of mass, because this is different than 0, no? Remember, that's the whole assumption. So it should be the initial minus the final is whatever is leaving, and this should be the H sub E. So again, what makes this problem a bit complicated is because you mix the first principle of thermodynamics with but you rewrite it. I mean, you rewrite the first principle of thermodynamics for a closed system in function of time instead of not having the dot. That's no difference. So now, okay, what do we need to find? We need to find the values for the U's, okay, and for M1. Okay, so let me, I'll do it very quick if you want. I'd rather spend more time on the next problem. So basically we have the equation. So we need to find N sub 1. What do we know from this problem? We know the pressure, we know the quality. So we know, for example, that we're gonna have to find V1. Okay, so we have to do a bunch of stuff. So as state 1, what do we know? We know T1 equal to 260 degrees and X1 equal to 0.7. So we can go to the tables. So table A2 in function of temperature. This one over here. So push down, push down. Why A2E? I don't want A2E. I want SI units. Here we go. So table A2 at 260. What do you have? U sub 1 should be what? U sub, you need to find the mixture. So UF, UG, you're going to need UF, UG. 260 is these two columns here. I think it's these two columns over here. Okay, so from the table, we're gonna have here that write down U sub F is 1128.4, U sub G is 2599. Okay, you can also write V sub F, that way we don't have to write it again. So V sub F would be equal to what? 1.2512 10 to the minus 3. Vg would be, no, it's 27, sorry, 1.2755. And V sub G would be 0.04221. Okay, so using this data, you can find that V1 will be equal to V fluid plus X1 Vg minus V fluid. And if you do the calculations, this gives you V1 equal to 29.93 10 to the minus 3 cubic meters per kilogram. And let's just do that once, and U1 will be equal to U sub F plus X sub 1, UG minus U sub F, which will give you a value of U1 equal to 2157.8 kilojoules per kilogram. Okay, but over here, let's not lose track of what we're trying to find, is to find M1. So by definition, what should be the mass flow? Is rho AV but we also know that what? The specific volume is what? Yes, it's 1 over rho, but in here we use the other notation is the volume divided by the mass, no? So we could say that this time would be divided by the mass flow here. So we know V1, what's given to us, here V1, we can know V1. So from here we can find M1 should be equal, so we don't try to find, sorry, we need to find M1. Sorry, forgot here. No, M.1, M1. So M1 would be equal to what? 0.85. No, yeah, 0.85, which is V1, divided by the specific volume that we find out to be 29.93, 10 to the minus 3. So this should give you a value for M1 equal to 28.4 kilograms. Okay, and the same thing now we have U1 that will be used in this equation. Okay, we have M1, U1 here. So remove, M1, U1. All right, so similarly, we can do, using the same idea, we know that V2 is going to be equal to V2 over M2. So we need to find what would be V2. And this is for the closed system. Which is this one over here. So what should be V2? Same thing as V1, no? It's a closed system. So we have V2 equal to V1. Now, in order to find V2, which will be VE, we know is a saturated vapor. But the temperature is the same. Okay? So in this case, what should you have? V2 should be equal to what? The value of V sub G which is the 0.04221. And if you want the U sub 2, that what we do at once would be the U sub G, which is 2599. Okay, so we can find M2 would be equal to V2 over V sub 2 would be 0.85 divided by 0.04221, which this one would be equal to 20.14 kilograms. And I'm just looking at the equation initially, and I mix the notations myself, so be careful here. So be careful here, because what I did is, I don't know how to resolve it now. Okay, wait, I'll solve it now. So now, what I want to say is that I put the dots, but maybe I should have not put the dots. So let's just recall that equation. So go to the next page. Okay, pay attention now, because I'm just going to rewrite the first equation, because I think I'm going to change something, okay? So this is for the closed system. So that equation, if we do it normally, should be Q minus work plus M1 U1 should be equal to M2 U2. And now what happens is that we have plus M dot E. That's where I got lost in track. So I'm going to modify this equation, okay? So again, the work here is 0. So this is going to give us Q. And here we say that the M dot E was equal to M1 minus M2. So it's the dot which are going to disappear. That's the only thing that happens. So we're going to have this is equal to M2 U2 minus M1 U1 plus M1 minus M2 H sub E. So basically, guys, what I'm doing, initially I put the dots, I'm just removing them, okay? Sorry for that. So out of this equation, I thought we had everything, but we don't have everything. We have M2, we have U2, we have M1, you have U1, we have M1, M2, no? But we need the H sub E. So what would be the H sub E? Again, you can look at the figure. What is the temperature over here? 260, no? So now we can go and say what? That the H sub E over here should be equal to the H sub G, no? Along this line. So again, this will be table A2. So we have H sub E will be equal to, so H sub G will be equal to 2,796.6. Okay, so finally, substituting into Q, we're gonna have what? Q equal to 20.14 times U2 that we say was 2,599 minus M1 is 28.4 times U1 that we find to be equal to 2,157.8. Should be the first term, plus M1 minus M2, so that should be 28.4 minus 20.14 times H sub E, which is 2,796.6. 796.6. And if you do the calculation, this gives you a heat transfer of 14,162 kilojoules. Okay, so problem 661. What do we know? A 2.64 kilogram of copper. So let's say M will be 2.64 kilogram. Maybe let me try to do this here. Zoom 125. That way it might be easier. I don't know. Okay, part initially at 400 degree Kelvin, so put T1 equal 400 Kelvin, is plunged into a tank containing 4 kilograms of liquid water, initially at 300. So basically we have here water tank, T water 1 is 300 Kelvin. So this will be T copper 1. So we plunge the copper here. This is water. And let's say, so T copper 1 equal to 400 degree Kelvin. And the mass is 2.64. What else do we know? The copper part and water can be modeled as an incompressible specific heat. So the copper and the water, okay, so part C should be C sub B, but just part C of the copper, C sub C will be 0.385 kilojoules per kilogram Kelvin. Things should be divided or not. I'm not 100% sure here. And C of water, CW, is 4.2 kilojoules of kilogram Kelvin. Okay, we'll check the units later on, respectively. For the copper part and water as the system, determine the final temperature in Kelvin and the amount of entropy produced within the tank in kilojoules. Ignore heat transfer between the system and the surrounding. Okay, so we need to find T final or T average and change in entropy. Okay, so if you remember, we kind of did a similar problem in class the first time we covered entropy. So over here, this one can be a little bit tricky, but what type of system would that be? Open, closed, or open, or control volume? Is the mass changing over here? No, so if the mass is not changing, that is a closed system, okay? So for the closed system, we can write the first principle of thermodynamics, which will be what? Heat minus work. In this case, should be equal, if we neglect kinetic and potential energy, should be equal to what? Change in internal energy. Okay? So this is important. Now, they say to ignore any heat of the system with the surroundings. So what does that mean? This is 0. Do we have any work done? So this is 0. Now, they don't say that to us, but I think we can make the assumption. Do you think the water is going to change its state, or is always going to remain on the same state? Water over here looks like it's going to remain on the same state all the time, no? So we can assume it as an ideal substance. If it's assumed as an ideal substance, what can you say about delta U? Would be approximately equal to what? MC, should be really C sub V, but MC, perfect, delta T. That's exactly what I wanted to hear. Okay, so really this equation here gives us what? Total change in internal energy is 0, but now if we develop that for each substance, what are we going to have? M, say copper, C copper, T final minus T copper initial, plus M water. They don't give us the amount of water? Okay. C sub water, T final minus T water initial, and this should be equal to 0. I probably forgot.
I think the mass of the water was 4 kilograms.
That's what I'm going to go back and look. Let's open this. Yes, you see, and a tank containing 4 kilograms of water. All right, so you see I forgot that. All right, so we know M water here is 4 kilograms. Okay, so from here we can solve. We have, so this will give us what? Okay, so let's solve here. Let's first factor by TF will give us M copper C copper plus M water C water will be equal to M copper C copper TC1. Sorry that I write smaller and smaller, but now this will be, I'm not going to be able to write it down, plus M water C water T water 1, no? So at the end, this will give us what? The final temperature will be equal to M sub C, C sub C, TC sub 1, plus M sub water, C sub water, T water sub 1, divided by M sub C, C sub C, plus M of water, C of water. Okay, so if we do the numerical application, all the units should be good. We have T final should be equal to what? Let's see, N sub C is 2.64 times C sub C 0.385 times T sub C1 400 plus 4 kilograms of water times 4.2 times 300 divided by 2.64 times 0.385 plus 4 times 4.2. And that should give us the temperature, the final temperature in Kelvin. So go ahead and do the calculation, please. 305.7? Yes. 305.7 Kelvin. Okay, so now, okay, on this system, do you think that now if we don't do any work. So you put the copper that was at 400 into the water, ends up with a temperature of 305. Do you think that now, can you get back the copper at 400 degree Kelvin without doing anything? No. So that means that the fact of putting the copper into the water is a one-direction process. So this should be non-reversible or irreversible, correct? So that implies what? That the change of entropy should be different than zero. So what is really happening is that when you put the copper, the hot copper in the water, the copper is going to transfer energy to the water, and that energy, the copper cannot recover it. Okay? So basically, the copper is losing energy, is wasting energy. Okay? Unless your goal is really to run the water, no? But in this case, would be this. Okay, so how can we prove that? All right, so I don't like the cooking, to need one equation and go and solve it. I mean, to go and then substitute the values. So we have a closed system over here. So what does that mean? First, that the mass is constant, but most important, that the volume is constant, no? Okay, so now, let's say, recalling the first principle of thermodynamics, which would be Q minus work, in our case, would be equal to M C dt. This should be the delta U. Okay, it's not N sub C, it's M multiplied by C multiplied by dt. And then, what is the definition of entropy? Change of entropy ds that is equal to delta Q over T. So if you remember when we did the TDS relation, I say here that delta Q is more or less equal to Q. So this will be equal to TDS. All right? I mean, now if I substitute this Q into the first equation, so from here we get what? TDS minus work equal to M C dt. Okay, what is work? By definition, what was work? What is the work done by the pressure? I mean, integral or no integral, it doesn't matter. It's PdV, no? If the volume is constant, what would be the work? The work done by the pressure? Zero. So this is 0. So this term is 0. So this means what? TdS equal to M dot C dt. Now, if I divide both sides by T, what do I get? ds equal to M C dt over T. If I integrate, let's say between S1 and S2, and between T1 and T2, I mean, we get basically here, if you want, I will do S2 minus S1. Okay, so now I'm going to have to expand. So we have the change for the copper and the water, no? So now we have what? Two terms will be M, let's say copper, C sub C. Maybe I'm going a bit too fast. What is the integral? Let me put it over here. What is the integral of d dt? It's log, no? Okay, so if I put here T1, T2, should be log of T2 over T1. So now, For the copper, what should I have? Log of T final, which would be T2, and what would be the initial? T copper 1 plus M water, C water, log of T final over T water initial. All right, so if we do the numerical application, this will give us S sub 2 minus F sub 1, let's say will be the delta S, will be equal to what? So N sub C was equal to what? 2.64 times C sub C 0.385 log. Guys, here I don't want you to give me the final result initially. I want you to give me the value for each one of these terms. Okay? So T final is 305.7 divided by the initial temperature of the cover is 400 plus 4 kilograms of water times specific heat of 4.2 times log of 305.7 divided by 300. So what does that give you? If we did it correct, the first one should be negative. No? Because what does it mean? The copper will be losing energy, no? What is that term? How much is that term?
Negative 0.2691.
Negative 0.2691. Okay. And now, if we did things correct, what should you get over here? Should it be bigger or smaller than that value? Should be positive and a little bit bigger, no? Because we know that by the principle of increasing entropy of the universe, this should be always positive. So hopefully it will be 0. Whatever. 316. So basically here, if you want, you can give me the difference, but I'm not that interested, is higher than 0, meaning that this process is non-reversible or irreversible. Okay, so I hope this problem was a good reminder of what we're doing before the exam. So guys, I think for material-wise speaking today, that will be it. I don't think we have time to do anything else, but during 5 minutes, probably I'll let you go. Let me give you a quick overview of what we'll be doing next. Okay? So let's open the book, the textbook. Let's go back all the way back to the beginning. So let me probably put 75. Let's see. Oh, this is what I wanted to open. Oops, why this is not opening? All right, let me just reopen the book. Hopefully we open properly. Okay, so this was control volume analysis, second law of thermodynamics, using entropy. This is what we have been doing. Okay, so the next thing we need to do now, we're solving problems with different compressors, turbines, and so on. Okay, but so far we were assuming what? That within the turbine or the compressor or the pump, you were not losing any energy, correct? But what is the real life? Is that if you put energy into a turbine, it's not going to be completely efficient, no? Okay, you're going to waste some energy. Okay, so we need to look at what is called about the now the isotropic efficiencies. How do you find the efficiency of a turbine? It's basically very simple. How much energy you put in, how much energy you get out. You're always going to get out less than what you put, no? Okay? So we need to determine the isotropic efficiency for the turbines, for the nozzles, which will be the same, compressors, and pumps. So we do that, but let's first look at the figure. So, okay, so I don't like too much that figure, but basically let's look at it. Let me magnify this. We'll do into detail next time. Okay, so the same thing that we had, the diagrams, the TV, the PV diagrams, we're gonna have similar diagrams that will be the H, S, or U, S diagrams. But basically they will have kind of the same shape, okay? So here what happens when you go to a turbine? What is the function of the turbine? You transform. Generally, what was the model for the engine on aircraft? You first have a compressor because you want to take the atmospheric pressure, compress it, so you increase the pressure. Then you burn the fuel, so you increase the internal energy, so you have pressure times whatever is the volume of the control volume plus internal energy. What is that equal to? The enthalpy, no? Okay. Now, what is the role of the turbine? Is to transform all that energy into kinetic energy. Okay, so you can push on the engine. No, that's why you have the air coming out is a lot faster than the air coming in, no? Okay, through the turbine. So basically, what does that mean? You need to go from a high pressure to a lower pressure. All right. So if the system is isentropic, and this is S, what does that mean? That we're going to go through the two lines of pressure that are these ones here, following a straight line down. Okay? So we go from here to here to be isentropic. This is S. However, what do we know? We know that that's not going to happen. Really what's going to happen is that you're going to go to 1 to a value 2 over here. That will be on this line. Okay? So what do you think will be? So you see this value here will be H1 minus H2, and this one will be H1 minus H2S, no? Okay? So probably if I go now here, let me close this. If I go now here, let's see somehow bigger. What would be the efficiency? Whatever you are supposed to get. H1, you go H1 minus H2 because H1 will be higher, so you want a positive value. H1 minus H2 divided by H1 minus H2S, no? Yeah? And basically that will be the efficiency of the turbine. So again, this is for the turbine. What is the turbine? You go from high pressure to low pressure, no? How would be the figure? Let's see if this is the one next. For the compressor, let's see, that's turbine. Hopefully the next one is a compressor. What is the function of, okay, nozzle is the same thing. Forget about that one for now. Okay, compressor. What will you do from a compressor? You will do kind of something similar. You will go from what? From a lower pressure to a higher pressure, no? Yeah? On the HS. So you do the same thing. Now you go. The isentropic will be going through this line. This time you see that H2S should be higher than H1. So the efficiency should be equal to what? H2 minus H1 divided by H2S minus H1. Probably the equation we're going to see next, no? The efficiency of the compressor is H2S minus H1, H2 minus H1. Okay? So what's going to happen from now on is that we're going to be solving the same type of a problems we have been solving, but sometimes they're going to give us that they're going to tell us on the problem that the efficiency of the turbine is going to be a certain value. So the efficiency of the turbine is a certain value. This will help us to find either H2 or H2S on the problem. okay? But the procedure will be the same. You just add an extra step on the solution procedure, okay? So I'm sure all that stuff wasn't that exciting, no? But basically that's what we're gonna be doing. And if you want, I'm not gonna record this part, and so I can close. So let's say here, cancel for now. And then what would be the goal of this? So for example, exergy, we're not gonna look at it. Let's say we go to the gas power system. So this would be, for example, an engine, vapor power. No, let's look at the Rankine system. Hopefully it's no. Rankine, you see Rankine here. Gas turbines, for example, for aircraft propulsion. Okay. I don't know which one we're going to calculate. So this would be the cycle. You see that, I mean, we already kind of studied this. This would be the cycle, but now probably they will tell you the efficiency of the compressor is that much, and the efficiency of the turbine is that much, the efficiency of the nozzle is that much, and you need to come up with a more complicated figure than this, no? Because with the isentropic, no isentropic efficiencies. Okay, so we'll see how far we get. All right, so we finish early today. Unless you have questions. Yes?
On assignment 6 for part B, or there's it's the last question on assignment 6, or assignment 6 part B. I keep getting the wrong answer, but I think it's because the tolerance is really, really small, because the number is really small. Like, have you heard of other people having that problem?
Yes. We know that in class.
Yeah, because we don't have a class. Yeah. Okay, so will we be?
What is it, 56?
Yeah.
Yeah, I mean, yeah, the 56 was, we're getting complete an answer different than the one of the, yeah. I think the 56, I get it every single semester, forget about it. We have it correct, they don't have it programmed properly, because it's not something you can program, because you need to look at the values on the table. So each one is having a different problem. So on each problem should be looking at a different value on the tables, and they don't do it. They think that they have some type of algorithm that can go, but there's no algorithm. You need to go and look at the present and the value on the table. So don't worry about it, okay?
Okay, so we'll get credit back for that one then.
I mean, at the end of the semester, I think I told you already a couple of times, I'm not really going to look only at the numerical value, okay? If you have completed all the homeworks and you have at least 80% in all the homeworks, I'm going to give you the full 10% for the homework.
Okay,
Okay?
thank you.
Yeah. So it's not that I'm going to be that big.